Hello there, welcome to my class. Today we'll talk about.
Hello once again. There is one other important thing that we can learn in the design combinational circuit, and that is the implementation of Boolean expressions using decoders. So decoders are not only used to convert information into its binary form, but also to implement Boolean expressions. Let's go back to our decoders. We have here an octal decoder. And based on our truth table, we can see that the equation for our output are mean terms. The advantage of using coders is we can have it as a single integrated circuit, like our octal decoder, which is oftenly called a 3 by 8 decoder. Observing our map, taking for consideration 0, that is actually a mean term, equivalent only to A prime, B prime, and C prime. Let's deal with 5 also. Then that will be only equal to A, B prime, C. The rest of the output of our decoder are mean terms. Since they are mean terms, we can use this output to implement different Boolean expressions. Let's take, for example, our 3 bits two's complementer, which we designed in our previous videos, where from our table, we tried to extract our equation using K-map, and we were able to get the equation for Z equivalent to C, Y be equivalent to B, X or C, and the equation for X, and implemented as this circuit. Looking into this circuit, however, we'd be needing at least 4 integrated circuits, one for our NOR gate, then we have for 2 input AND gate, and another for a 3 input AND gate, and our 3 input OR gate, and another for our inverters. We can, however, reduce the number of integrated circuit we are going to use to implement the circuit if we are going to use octal decoders. How? By simply getting the equation for our output x, y, and z without even simplifying it. For x, for example, that will be equal to 1 ORed with 2, ORed with 3, and 4. While y will be equal to 1 ORed with 2, 5, and 6. And our z will be 1 ORed with 3, 5, and 7. Why do we use octal decoder? Simply because there are 3 inputs. Let's try to implement now the equation of our output using an octal decoder. For x, it will be only 1, 2, 3, and 4 ORed together. And y will be 1, 2, 5, and 6 ORed together. While z will be 1, 3, 5, and 7. Let's try to simulate it. Let's take, for example, 3. 3 would mean that our output of our decoder 3 will be equal to 1. With that, our output x will be equal to 1 and our output z will be equal to 1, where y will be equal to 0 since y is not connected with 3. So our output will be 1, 0, 1. Is that correct? As we can see here, the 2's complement of 0, 1, 1 will be equal to 1, 0, 1. Let's take another. For example, 6. That is 6. Expected output is 0, 1, 0. So 6 will be 1. So y will be equal to 1. And there is no other gate that is connected to 6. So therefore, this will be 0, 1, 0. Is that correct? 0, 1, 0. With this, we will be implementing a 3 bits two's complementer using only a minimum of 2 integrated circuit, 1 3 by 8 decoder, and 1 quad 4 input OR gate. Let's try to look our traffic light malfunction detection circuit. When we try to simplify our equation, again using K-mapping, we were able to obtain the equation for M to be equal to AB plus BC plus AC plus A prime B prime C prime, and implemented it using 4 AND gate and 1 OR gate. If we are going to analyze how many integrated circuit that we'll be using, 1 for inverter, 2 for the 2 input AND gate, 1 for the 3 input AND gate, and another for the 4 input OR gate. If we, however, use again an octal decoder, the equation would only be equal to the summation of 0, 3, 5, 6, and 7. That will be equivalent to 0, 3, 5, 6, and 7 ORed together. 0, 3, 5, 6, and 7 OR together. We are going to get to what will be our output. Our output will be equal to 0, meaning there is no malfunction. 2 is equal to 1. Since 2 is not connected to our OR gate, then our output will be equal to 0. Let's get 5 is equal to 1 and it's connected to our OR gate, therefore our output will be equal to 1. If we try to compare this implementation circuit with that of our previous circuit, then we could say that using an octal decoder is a simpler circuit. How about our full adder? Can we also implement our full adder using only a decoder? Again, since we are trying to add 3 bits, what we need would only be also 3 by 8 octal decoder. Let's look back into what is the circuit that we use in our full adder. So our full adder, the sum is equivalent to x NOR with y, x NOR with z. Then we have our sum, which is equal to this. And again, as we try to look at it, we'll be using so many integrated circuit. Unfortunately, we said that this is not the actual circuit that we are trying to use in a full adder. Instead, we use these 2 half adders with the carry OR together. So if we are going to use an octal decoder, what will be the equation for C and what will be the equation for our sum? So for our sum, that will be equivalent to 1, 2, 4, and 7 OR together. And for our carry, that will be 3, 5, 6, and 7 OR together. Mean that for our sum, that will be 1, 2, 4, and 7 OR together, while our carry will be 3, 5, 6, and 7 OR together. Let's try to simulate it. Let's try 3. So 0, 1, 1. So 3 will be equal to 1. Since 3 is connected only to C, to the carry, then the carry will be equal to 1 and the sum will be equal to 0. Is that correct? That our carry is 1 and our sum is 0. Let's try what? Let's try 7. 7 is connected to the sum and also connected to the carry. Therefore, our output is equal to 1, 1. With all our examples, we can conclude that if an equation is in its canonical form and that is in sum of products, then it would be very easy for us to implement that equation using decoders. So try this on different Boolean expression which are in its canonical form and in sum of products. Hope you learned a very important application of our decoder in this video.